This is a video clip in a series of system identification course. This video clip belongs to the chapter of models, and we will give some basic examples about two types of model that we will use a lot in this class, and these are state space model and time series model. So what we're going to discuss is actually the model system description, its property, and some useful properties. So let's start with the state space models. Here we focus on uh, linear time invariant and discrete time state space model. And the general form can be expressed in this. We call X the state variable. We call U the input deterministic one. And here in the context of system identification, this is the input signal that you will design so that the system identification experiment is valid. WT here we call the process noise. At the output equation is a linear function of the state variable, and you have the measurement noise. So from the linear control system theory, we have this well-known property that usually we call a group of these matrices that are system matrices. Sorry, I missed one term, that the process Y, the output equation, must contain the direct term, the feed-forward term from the input. So this is called system matrices from linear control system theory. The pair A and B will explain system controllability, and the pair A and C will explain the system observability. So the controllability is a property of the system where you can drive the state variable, from a starting point to be anywhere in the Rn plane by choosing appropriately the input signal. Okay, if you can always do that, we call that the system is controllable. Observability is a problem where you would like to examine whether if you just observe the output, can you always estimate the initial condition or not? If you can do that, we say the system is observable. And that property can be just be examined from the pair of these system matrices. In the context of estimation theory, when we use the space equation like this, the process noise and the measurement noise are often assumed to be white noise sequence, and which again means that the expectation of WTWS will be 0, okay, when P is not equal to S. And the process and the measurement noise may have correlation, and that's what we assume here, that the covariance of these two noises are explained in this covariance. In this slide, I would like to we would like to look at that way. Or if A, B, C, D, and these covariant noise are given, okay, what are the properties of this model, of this system? We have this one important result that that talks about a stationary property of the space equation, because you can, of course, we call X state variable as as signal, output signal, but we can also regard it as a random process, because these are the signal that is corrupted by two random signals, W and V. Which means if they are random process, then we must talk about stationary property, so that it allows us to talk about other things. Right? So the very first result is that if the matrix A is stable, since W and V are assumed to be white noise, which also imply that these two guys are Y sense stationary. These two guys are stationary processes. Then we can show, actually this is a theorem. It says that the process X and Y are Y sense stationary in steady state. Okay. I'm just gonna put the the result on the state variable only. Because the output equation is just linear in X. Okay, so you can just develop the results on your own. Let me put a note here that when we say the process X is Y sense stationary, it only Y sense stationary in steady state sense. So what does it mean exactly? Remember that when the system is not stationary, it means that covariance function or correlation function. This is correlation function. This is covariant function. If the process is not Y sense stationary, this guy can be a function of t of s, right? But if they're Y sense stationary, it's going to be a function of t minus s only. So that's the definition. So come back to the result to say that X is Y sense stationary in the steady state sense. It basically means that if you examine the covariance of X, covariant function, by using the two time indices t plus k and t, if you allow t to be large enough, asymptotic sense, okay, these covariance function will be depend on k only. And it is a function of a to the k. This is for positive time index, and this is for negative time index. So this is matrix A to the K times the matrix sigma X. And what is sigma X? Sigma X is actually the limit of covariance at time t and t. So basically, it means that Z0 exists. If the limit exists, okay, Z0 exists, and that is our notation sigma X. The nice result from using the state space is that, the covariance, at covariance function at the time gap 0 can be numerically obtained by solving the Lyapunov equation that use the system dynamics A, system dynamic matrix A, use the input matrix B, and Q, of course, Q is the covariance of the process noise. And what you know is that Q is positive, right? So this guy, B transpose is positive semi-definite. The Lyapunov equation is a very famous, well-known, has a wide range of applications in linear control system theory. Let me state the results of the Lyapunov equation that says, okay, if you have this term, positive semi-definite, and if A is stable, when you solve this matrix equation, sigma X, there exists a positive solution. And that's a nice result, and that is a valid result because you also aim for a positive solution sigma, because this sigma represents the covariance function at time 0. It's actually the covariance matrix of the process X. Okay. So once you obtain sigma, you see that your covariance function at time gap k is going to have the decay rate as the same decay rate as a to the k. And because from linear algebra result, you know that a to the k, its dynamic will depends on the eigenvalues of a. So the covariance function will decay fast or not, depends solely on the locations of the pole or eigenvalues of a. If it lies near the boundary, what is that thing? This is called the unit circle in the complex plane, because Again, let me emphasize that we consider the discrete time process. So when we talk about stability, uh, we refer to the region inside the unit circle. Come back again. If lambda a or if eigenvalues of a are marked near the boundary, it means that of course the eigenvalue is gonna decay very slow, and what you're gonna see uh, at the covariance function is something like, oh, it gradually decays. So it's more like, oh, the process is nearly non-stationary. Okay. On the other hand, if your eigenvalue has a very small modulus, like 0.01, you know that these things, the closer to the origin, the eigenvalue, the closer to the origin, the faster it decays. Right? So what you're gonna see at the covariance function is it's gonna decay very fast. Please refer to the basic property of the covariance functions in the video in the appendix of my book. You know that of course z0 will have the maximum value, and c at time tau will be always less than z0 for tau different from 0. This is for of course for Wisen stationary process. All right. So this is a very nice results. So that means we will see very related results, how one can suggest stationary property of a time series model. So we can just connect to the concept of state space system. There's another form of state space model that is actually useful, and actually it becomes a standard form for several estimation methods. One particular case is a subspace identification that we will see in the following chapters. Okay. This is called the innovation form. Okay, let me just state the results first. One thing you should recall is that you can have many state space representation for the same system. You should know that there's from a change of coordinate, right? This is by using a transformation T, you know that you can derive the state space equation for T, and of course you can have different system matrices, but by knowing the transformation matrix T, you can just go back and forth to from this coordinate to another coordinate. Okay, this is a concept from linear system theory. Then this slide suggests that okay, there's going to be one particular equivalent state space form that is called innovation. The state variable in this form is x hat. And the system dynamic is actually the same as the standard one, A and B, okay? But it has extra term K times ET. That actually the whole thing represents the process noise. And if you look at the output equation, okay, is y equals c hat t, c x hat plus et. So this is measurement noise. One thing that is different from the standard one is that in the standard one, the noise contains two terms separately. Okay, but these two guys, they are correlated, W and V. In the innovation form, it has only one term in the error. So how do we come up with this innovation form? The motivation, there's a long story for that. Actually, there's a problem of one would like to estimate the state variable xt if you only observe the sequence yt, the measurements. Again, let me mention that I have some typo in the slide. Um, there should be the feed forward term of the input here as well. Okay. All right. Okay. So the problem of estimating t using the information of the output, the measurements, right? We call the measurement because that's the only signal we can measure. State variable typically represents a signal that explain the dynamic of the system, but not all of them can be observable. Okay. So so the notation x hat actually, which is a state variable in this form, actually represent the estimation of xt. Okay. So if we can estimate x, I mean, it's very natural to say that, oh, to predict y or to estimate y, we just use c times x hat. Of course, we don't want to add up the noise term or anything because this is what we're gonna do. We're gonna estimate, right? You want the estimate to be close to y, so we don't add the uncertainty term or whatsoever. Then, when you perform such approximation, um, so you call this guy y minus y hat as the error term. And because the way we estimate that, I mean, we didn't explain in detail here, but the estimation method here is the best one, the optimal one in the MMSE sense, which means the estimate x here give the minimum mean square error. And the method is actually proved by Kalman, mathematician. Um, So ET is called the innovation. It represents the residual error after you do the best prediction of Y. So the innovation form basically suggests um, the actually suggests the observer form of X, and the information that used is actually the error. You perform the prediction, the estimation, and compensate E in the state equation by allowing this matrix K, which is called the Kalman gain, to compensate such error. Of course, if the error is big, is amplified by the right amount of the matrix gain K to say that, okay, the X hat at the next step should be, this value, blah, blah. Okay. So to obtain the Kalman gain K is not trivial. That's going to be, and again, another story. The theory behind it, Kalman gain will be solved from what's so-called Ricardo equation. But we would like to omit the detail here. All right. So basically, the key message here is that I just want to mention that we can always we can transform the standard state space model into the innovation form. Okay. Now, in the sense of system identification, of course, you're gonna look at this A, B, K, C as free parameters that you're going to estimate. And if you're going to use this form, there's only one error term, ET, in the equation. Okay, that's I think that's all for state space model. If you watch this video clip, is a nice exercise if you can just generate ABC by yourself randomly, but make sure that you generate the matrix A that is stable, and try to simulate the response of X and Y. Okay, when you of course randomly generate the noise sequence of W and V. You can come up with the noise covariance matrix, and you can compute the covariance function using the software, and see if they behave just like this property. Okay. The next group of the model is actually contains so many models, very useful in time series analysis. It is called time series models. We're going to start with the most general one. These time series models can split into two main groups, stationary one and non-stationary one. Okay. In this course, we will particularly focus on the stationary one, but I also in this clip I will also give one class of non-stationary one that use a lot in the analysis as well, ARIMA model. So let's talk about ARMAX process. ARMAX stands for autoregressive moving average, right? Autoregressive moving average with exogenous input. So the equation involve two kind of inputs, deterministic one or exogenous one. I mean, in system identification, we call it deterministic input, but in the time series analysis, they call UT as exogenous. E is a noise, and again, often assumed to be white noise with covariance sigma. All these A, B, C, these are matrix polynomials. The dimension just whatever dimension that fit to Y. If Y is a vector of Rn, a polynomial is n by n. Okay. If U is Rp, of course, B is going to be matrix B is going to be n by P. Things like this. So all these coefficients are matrices. Let me make one note that the matrix polynomial A will start with I because you're gonna have okay, we will look at the time the time domain equation later, but let me note here that matrix polynomial B start with the first lag operator, which means when you apply BL on UT, the first term that appear will be UT minus 1. Okay. YT, the response of YT will be an effect from UT minus 1 from the past. And C for the C polynomial, it starts with I, which means it represents that, okay, there's going to be some instantaneous effect from ET to YT. If you apply these matrix polynomial to the time domain to obtain the time domain equation, this is called ARMAX process. And we use the notation ARMAX P, okay, the order of autoregressive process, Q, the order of, this is what we call moving average process, and M, okay, M is the order of a term with the exogenous input. It's called autoregressive AR here because Y depends on the past of itself. It's called moving average here in this term because it's like the average of the noise in the past. And of course, X is from exogenous. All the coefficients A, B, C, and the noise covariance form the parameter vector. We would like to estimate the whole thing. Of course, ARMAX model is a more general form of time series that belong to the stationary class. If you just get rid one term in the equation, you get like 4 special cases. Okay, the first one, ARMA process, is the one without the U term. All right, AR process is the one without what? Without the U term and without the moving average one. Okay, and so on. So let's see one by one. So ARMA process with order P and Q will contain only autoregressive term that depends on Y, and the moving average term depends on the instantaneous noise and the noise in the past. Autoregressive process is only defined by the order P. By the name suggests, it only depends on the past of YT itself, and there's going to be a direct term on E. Moving average, YT depends on the past noise and instantaneous noise. Okay, from moving average process, it can be readily suggested that because y is actually a weighted sum of noise, right? If the noise is stationary, which is of course, sorry, if the noise is assumed to be white, which means that it implies that the noise is stationary, then you have a sum of you have a finite sum of stationary process. Then imply readily that y is also stationary. In this slide, I use the term stationary. So please be reminded that it's a term y since stationary. I would like to skip to ARX. Okay, ARX model is the one with autoregressive term and the one with the exogenous input. Last one, finite impulse response. This is the one we use in engineering. So it's the one suggests that y depends on the path of deterministic inputs. There's a relationship between, one time series model to another. This slide, I would like to give a connection from AR of first order to the moving average process. It's very simple. This is AR1. Okay, so YT depends only on the first order lag of Y. Okay, so if you just keep writing the sequence of YT minus 1 as AT minus 2 plus ET minus 1. Okay, so you're gonna get A squared and you get AT minus 1. But then you just keep writing this again, YT minus 2 in terms of YT minus 3 and so on. Okay, you're gonna see that, oh, actually you can get rid of the variable YT. So because the expression of E, the past of the noise appears, then you can say that, okay, I can write it as an infinite sum of, a to the power of k, et minus k. But then even that you can just write this recursive equation like this, the result is only valid if this infinite sum converge, which means that somehow we implicitly assume that a to the k should be decaying, right? Otherwise, this infinite sum cannot converge. So that implicit assumption is that, okay, your eigenvalue, the modulus of eigenvalue should be less than 1. Then by having this result presented, you see that you can view autoregressive process as infinite moving average. Okay, because that's like, oh, that a coefficient, this is like of coefficient ck to c et minus k, but the infinite term. Autoregressive process appears a lot in application, so it's interesting to see it from another point of view. These handouts, on this slide, I would like to represent it in the state space form. I think from our background, given a recursive equation or given a difference equation, right? For example, difference equation like this, there's a method, there's a straightforward procedure to define the state variable and represent it in state space form. Okay. And this is what we do. We define the state variable as all the p lag output y, t minus 1, t minus 2. Then you just go on, keep writing. So xt plus 1 equals yt minus 1 dot 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 yt minus p plus 1. Okay, and now represent it as a state space form. This is the dynamic matrix A you're gonna get. So you can say, oh, this is xt minus plus 1 equals big A x plus b et. So the AR process turns out to be just a state space equation where you look at the white noise process as the input. And of course, from the linear control system theory, um, the dynamics, right, the behavior of state variable would would solely depends on eigenvalues of A, and the eigenvalues of A can be solved from characteristic equation, the determinant of Zi minus A. So if you just expand it out, it actually turns out to be the determinant of this matrix polynomial. Okay. So if you, of course, the results from the linear control system theory is that if the eigenvalue lie inside what? Lie inside the unit circle, the matrix A is stable. But because this is not deterministic system, this is stochastic system because we have the noise term here. So if we refer back to what? To state space, right? That we just talk about stationary property. Let's say if A is stable, the process X and of course what? Ry sense stationary process in steady state sense. So come back here. It means that what we derive from for AR process is that if you find the root of this characteristic polynomial, then if eigenvalues lie inside the unit circle, then the AR process is Y-sense stationary. Okay. Now let's talk about moving average model. Moving average model. Okay, let me write. This is AR. All right, and this is moving average model. So it seems like it looked like if you just basically inverse, right? Inverse the AR process. It looks as if that you can obtain the equivalent moving average process. And actually, there's a relationship between MA and RA, and that we're gonna see as we're gonna see from this example. Now let's say I have two MR processes. Okay, the one described by Y and the other one described by X. If you notice, of course, the coefficient CK is looks like the reciprocal of one another. This is 1, 5, this is 5. Okay. For the equation of Y, it looks like the coefficient here is 1, 5, but the variance of noise that corrupted here is 25. For X, the coefficient here is 5, but the variance of V is only 1. We can quickly examine that actually the output of X and Y have the same spectrum, which means that you observe the second property of this process to be the same. So let me recall the results of the spectrum of stationary process. Please recall to the video that review stochastic process. If you have a system H, you have U, you have Y, okay? The spectrum of Y is actually given by the transfer function H times the spectrum of U times spectrum, times the transfer function complex conjugate transpose, or the Hermitian operator. Okay. So if for HY, if we just sketch it real quick, HY is gonna be 1 plus 1, 5, right? E to the minus I omega. Let me recall that this is 1 plus 1, 5, Z minus 1, right? And when we compute the spectrum, we take the value of Z equal E to the I omega, because this is discrete time. Okay. So the spectrum of Y would be what? let me write it here, 1 plus 1, 5, e to the minus omega, times spectrum of E, which is 25, times H complex conjugate transpose. So it would be this. What about the spectrum of X? Let me sketch here. Spectrum of X, transfer function of X is going to be 1 plus 5 z minus 1, right? So spectrum of X would be 1 plus 5 e to the minus I omega times 1. The spectrum is 1 times 1 plus 5 e to the I omega. You see that after you work it out, the green term and the yellow and the blue term, they are the same thing. Okay. So these moving average processes have the same second order property. You observe the same spectrum, but each of them, when you take the inverse, it corresponds to two different AR processes. So if you take the inverse of the moving average moving average process, you get AR, right? And of course, when you take the inverse, basically you can just take a look at the equation and swap the role of input and output. Okay, so the first one, I should use the yellow, the blue. So the first process corresponds to this AR. The green process corresponds to this AR. Then you see that the coefficients that correspond to the AR process are different. One is negative 1.5, the other one is negative 5. Which AR process is stable, is stationary? Of course, this one, because minus 1.5, right, lie inside the unit circle. So then it comes to the definition, right? That of course you have AR processes, two processes that have the same spectrum property, but when you inverse, it gives you different AR processes. One is a stationary one, the other one is non-stationary. So we say the MR process is invertible if when you take the inverse, it corresponds to a causal infinite AR representation. And that's the one with the that has a stationary property. So this is the term invertible. Now let's give some terms about ARMA process, some property of ARMA process. Of course, ARMA process is in this form. Y depends on the noise without a deterministic input. The process is stationary if you find the root, the determinants of this guy that lies outside. You need if the root of the determinant of AZ lies outside the unit circle. Please notice that there's a slight difference between this polynomial and the one with the one on this slide. Hold on. The page. And the one with this. I mean, you can just factor out the term z to the p. So I would like to mention that this condition, we want the root of this one lies inside the unit circle. But because of that expression is actually represented as the reciprocal of the root of as the root of the blue one. So the root of the blue one must lie outside the unit circle. I represent it in this form because most of the time CUEE textbook refer to this one. They refer to this format so that you can have results, non-results in 2 points of view, one from control system point of view and the one with the time series analysis point of view. Okay, so a process, any process is said to be causal if it can be written as some coefficients time noise in the past. This is YT. This is a linear combination. It can be infinite sum, but it's only the sum of noise from the past. So that is a property that is called causal. Then we have the result that for ARMA process, the ARMA process is causal if the roots of this polynomial lie outside the unit circle. If you wonder why, I suggest to read the books on time series analysis. And the ARMA process is invertible if the roots of the MA polynomial lies outside the unit circle. Okay. Okay. Now we have basically give some example of the space model, stationary time series model. Now we move to the group of non-stationary models. Okay. Let's just see some easy example. This is a process called random walk. The random walk is actually, if you look at this equation, is AR process of first order. Okay, but the coefficients here on the x, the coefficient is 1, right? So obviously this random walk equation is not stationary. It's called random walk because you move here from here. So you perturb your step, right, by the white noise. So this is t minus 1, this is WT, this is your next step. White noise is the most unpredictable noise or signal, right? So it means that at each step you take, it looks very random. That is called random walk. Then we say that we conclude that random walk is not stationary because the AR coefficient here is 1, and 1, of course, 1, it doesn't lie inside the unit circle. So this is an unstable linear system, right? But then, interestingly, if you take a difference, if you put the xt minus 1, that gives you the white noise sequence. That turns out to be stationary process. We can use this trick that is called differencing to some signal that it seems that this signal has a static trend. When we say static trend, it's something like this. You know that this is time t, all right, xt. If you have a function a plus b, it looks like this. Okay. If you add the noise, so this is what you're gonna see, right? So if you see data in applications, you observe that, oh, there's an increasing trend, and that trend seems to be linear. Okay, so it might fit to this model. And of course, this linear static trend is obviously non-stationary because the mean, the mean is a function of time, right? Recall to the definition of Weiss stationary again, okay? That the mean has to be constant. This covariance function has to depends on the time gap. And of course, the Weiss stationary is a weak sense of stationary. If the weak sense is not satisfied, of course, we don't need to talk about the strict sense. Okay, you see that when you have a linear static trend, the differencing still works. If you subtract xt minus 1 from xt, okay, just work it out, then you get the constant b, and then you have the difference term in noise. Oh, this is moving average process with a constant mean. But that constant, of course, is not dependent on time. So it seems like, oh, there's a nice technique, very simple differencing, and that becomes a tool in and that becomes a part of non-stationary time series model. So we define, of course, we use L as a lag operator. If I come back here, of course, if we represent it as a lag operator, this is 1 minus LXT. Okay. So if we perform 1 minus L, okay, to the power of D, it means that you perform the difference operator for D times. We say that a series X is integrated of order D, okay, if after differencing for n times, these differenced signal become stationary. So for random walk, obviously is a first order integrated model because you take the difference for one time. You can use a lack of differencing to reduce a trend, static trend like this as well. Maybe you can generalize it in a way that, okay, what about if you have quadratic trend? What would you do? Okay, think about it. Or you can use the differencing operator for removing seasonal effect. Okay, so something that has seasonal effect, like, you know, a year that has 12 months, you may have apply 12 lag operator of differencing. Okay, this is some example I taken from time series analysis textbook. Okay, your Y1 is a first order AR process with coefficient 0.4, which is of course obviously stationary. So we say that, oh, is I0 is integrated model with zero order, because we need zero order differencing. This is how it looks like for stationary process, AR process. But then if I make a cumulative sum of Y1, right? If I make a cumulative sum, of course, this Y2 has to be integrated process of first order, right? Because from Y1 to Y2, I make a sum. So in order to go back to Y1, I need to take a difference of Y2. Okay, and that's how it looks like for first order integrated process. It has an effect that is called no exact reverting. And then if I further make a cumulative sum of Y2 to get Y3, then that process is integrated process of second order. Now it has a momentum effect. It swing like this. So this is kind of a reverse engineer process. You start with a stationary one, and then you try to see, oh, how it looks like when it becomes non-stationary. But on the other hand, in application, what you're gonna see is it might be something like this. In application, you obtain data. This is how you plot in the first place. Oh, my data set look like this time series. If you see a time series look like this, that, oh, it has a momentum effect, maybe you want to try to make, you know, first order difference. And then when you go from to the pink one, you see that, oh, the signal doesn't fluctuate to have a constant mean. Oh, maybe I try to make another difference. So that's why you go to the first one. Okay. And then when the first one appear, looks like, oh, this looks like a stationary process, then you can say that, suggest that, oh, my original process might be second order integrated process. Okay, that comes to, when we know about the integrated process, now it comes to non-stationary model that is called ARIMA models. ARIMA model with the order PDR, PDR, is ARIMA model if you take the difference of X and it becomes ARMA process. So with this notation, Okay, take a look at this. The one in the bracket term, this is what? The series of yt is obtained by take differencing of x for d times. Of course, yt becomes stationary. And yt becomes stationary, but yt obeys these dynamic that have autoregressive term and moving average term. So yt is ARMA process. And that's what we call x is ARIMA process. So here's one example. If we have an equation like this, okay, you see that when you move xt minus 1 here, you can represent it as 1 minus lxt. This is 1 plus cl et. So what is it? Oh, after I take one order differencing, it becomes a moving average. So it's ARIMA process with first order differencing, first order MA. How about this one? How about this one? If you move it here, is 1 minus AL xt, right? And then you have another term. So it looks like, if you arrange the equation, it looks like you make a differencing of x once here and another one here, 1 minus AL. What? After take one order of differencing, oh, you have this appears as autoregressive polynomial. So this is ARIMA model of first order differencing. Sorry, ARIMA model with first order integrated and with AR term of first order. Okay. This is some example, time series of log CPI, consumer production index. Now see, you see, it looks like there's a trend, there's a drift, right? So you may want to try first order differencing. But still, this one, it doesn't have the mean reverting effect, okay? Because I mean, stationary process should look like, okay, up and down, fluctuated over a constant mean. So that's why maybe you try to take another second order differencing. And then from this, it just based on your pre-analysis of the time series. Then you may suggest, oh, that might fit to integrated process of order 2. And then you further fit it to, you know, ARMA, and of course the way you pick P and R is another big issue in time series modeling. There's a result that pre-examine correlation signal. People call ACF, all right, autocorrelation function. It's actually our RT in the analysis. Okay, because there's a result that, okay, if you derive the autocorrelation function of AR, it should look this shape. For MA, it should be something like this. Okay, so you can use that known result that derive mathematically from the equation, and then you try to fit it with the empirical result obtained from the data, and see how you can choose the effects of autoregressive and the effects of moving average appropriately. Next, the last topic about choosing the model is the issue of uniqueness properties. Okay. When we come up with a model class, then we may have question if, you know, how can we get the system adequately and uniquely? So in order to formalize things up, we define the set D as a set for which, or this is in the format of a general structure model, right? G is a transfer function with U, and H is a transfer function from E, and okay, lambda is the covariance of the noise E. Okay, so basically we define a set for theta such that these G had the approximation, of course, These estimated model give a perfect description of the true system. Okay. Mathematically, it means that G hat U equals GU, H hat U equals, HE, okay, and then lambda hat equals lambda. This is what we mean, give a perfect description. So there's only 3 possibilities when we define this set. This set is empty. We cannot find a single parameter that satisfies this matching system description, which means you under-parameterize the set. The model class is just too simple to describe the true system. The second case is that, oh, the set D has a member and it contains only 1 point, which means you can find only one set of theta that gives this matching. And it is a desirable property, which means the parameter that is obtained is obtained uniquely. The third one means the set D contains several points or over parameterization. Maybe your model class is too big, is too flexible. There's many other choice theta 1, theta 2 that give the same matching equation here. Okay, we can just illustrate that non-uniqueness property from state space models, because it's I think it's kind of obvious result we know from linear control system class as well. If you have one state space equation in one coordinate, let's say that, oh, you have another state space equation in another coordinate where these A and A bar are related by similarity transform. The matrix Q is some invertible matrix. You can just work it out. This is not too hard. Okay. At the output equation, okay, the measurement noise are the same. Okay, but the equations of the state equation are different. The process noises are also different. The point here is that, okay, the system dynamics are different from these two state space models, but we can derive the transfer function real quick. Okay, G is C, Q, the shift operator. You can work with Z as well if you want. Okay, Zi minus A inverse. If you just compute the transfer function of the system in the Z coordinate using, you know, everything is bar here. But because of this relationship, these the system matrices from two coordinates are related by this. If you just plug it in, CQ inverse, A bar is QA, Q inverse, B bar is QB, just work it out. Some cancellation occur. It happens to be the transfer function you would derive from the first state space model. Oh, we get the same transfer function. You can also look at the second order property as well. Remember that you can derive the spectrum by using what? By using the property that we know. This is what? The transfer function. Okay. I don't want to involve these too much, but the whole point here is that spectrum you derive from one model is the same as the spectrum you would derive from the other model. And that means when you estimate the state space model, just keep in mind that you can always obtain another set of parameters just by using the similarity transformation. Choosing the model structure, you have to be concerned with several factors. You look at the flexibility. If the model is, contains sufficient degree of flexibility or not, in order to explain your physical system. Okay, if your physical system is complex, maybe it doesn't make sense to use first order, such a simple model. But at the same time, you wouldn't go to you didn't want to use too much complex model, because you should be concerned with the uh, what, with the storage, with the computational complexity, and you should be concerned with the overfitting problem as well. And that means that you rely on the parsimony principle. You aim for the smallest number of free parameters as possible, as long as it can explain the data, adequately. You should look at the algorithm complexity as well. Sometimes you use complex model, but it also requires a higher computational cost. So please keep that in mind. When you choose estimation method, that plays a big role in your estimation problem. The criterion function, where you examine that, oh, my model is good enough. When you say, oh, it's good enough, it looks like that you minimize something. You minimize MSE, right? You minimize the negative log likelihood. So these are criterion function. Those plays a role in the algorithm that applicable to solve the problem as well. Okay, so we come to the detail of this when we talk about the estimation process. So I think that's all for the uh, description of models in this chapter.